You want me to do? Yeah. Hello everyone. Welcome to the Crypto Cafe. So I'm very happy to have Bardia, who is a PhD student in computer engineering department at FAU. So today he's going to talk about two birds, one stone, a unified high-performance entity architecture for ML-KEM and ML-DSA. Over to you.
Okay, hi everyone. In this session, I want to talk about post-quantum cryptography and considerations on hardware implementations of these two schemes, especially ML-KEM and ML-DSA as two NIST standardized cryptographic schemes for post-quantum era. So this is my outline. First outline of my talk today. First, an introduction to the post-quantum transition. And then we will talk about the entity, the most important part and hardware block of these two schemes, actually the module-lattice-based cryptography schemes. And then the differences and the challenges of a unified design that can support both of them, both ML-KEM and ML-DSA on a single unified core on FPGA or ASIC on hardware, actually. And then I will talk about several of my papers, my attempts to reach this point of a unified design, and then the challenges and the conclusion. So, as I think most of you know, we have several hard mathematical problems right now, integer factorization problem for RSA, discrete logarithm problem for Diffie-Hellman, and elliptic curve discrete logarithm problem for elliptic curve cryptography. And you know, all of them will be broken by quantum computers. So if you have a quantum computer, all of the traditional schemes or all of the current schemes will be broken. Because we have Shor's algorithm. Shor's algorithm is an algorithm that can only be executed on a quantum computer. So the problem is not because the power of quantum computer, it's because its capability of executing some special particular algorithms like Shor's algorithm or Grover's algorithm. So Shor's algorithm can solve all of these problems in a polynomial time. So if you want to enlarge the number of, increase the number of bits in public key or private key, it doesn't help you. So you need to find another scheme that will be safe and secure even on a quantum computer. This is post-quantum cryptography. So we are not talking about quantum computers. We are talking about some solutions after we have quantum computers. So because of this threat, NIST started a competition 10 years ago, actually 10 years ago, and several submissions has been, several papers have been submitted on their website. And after 3 or 4 rounds, after 3 rounds, actually 2 schemes has been standardized, has been selected as the winners of this competition. ML-KEM has been standardized in FIPS 203, and ML-DSA has been standardized in FIPS 204. ML-KEM for key exchange and ML-DSA for digital signature. And these 2 schemes are secure even on quantum computers. And both of them are based on module lattices. These are all the schemes that has been standardized or will be going to be standardized in the future years, in the next years, maybe the next year or even this year. ML-KEM, ML-DSA, and SLH-DSA has been standardized and published as FIPS 203, 204, and 205. HQC-KEM is an alternative to ML-KEM, and the standardized version will be published next year. And Falcon or FNDSA is another scheme as an alternative for ML-DSA. And these are the alternatives for public key cryptography. Instead of RSA, elliptic curve, or Diffie-Hellman, we have to use ML-KEM or ML-DSA. For AES, we can use AES 256. AES 256 on quantum computer is as safe as AES 128. So it's secure. AES is secure. We can reach the security only by increasing the number of bits. This is a timeline for transitioning for the transition to post-quantum era. As you can see, RSA and elliptic curve will be deprecated after 2030. After 2033, you won't see RSA or elliptic curve anywhere in the world. Everyone have to migrate to post-quantum cryptography. And this is for the US, mandated by NSA. Around the world, as you can see, 2035 is the last year of traditional public cryptography. So we have these two schemes, ML-KEM and ML-DSA. ML-KEM for key exchange mechanism, for handshake. Before encrypting using AES, you have to exchange the keys between two parties. So you have to use ML-KEM after 2030. And in these years, you have to, after 2025, you have to use a hybrid version. Everything have to use a hybrid version of elliptic curve and post-quantum. And ML-KEM is based on module learning with error. It's a version of learning with error on modules. Modules, we can, in simple words, we can say that modules are like vector spaces, but on finite fields or rings. In simple words. And so ML-KEM has a ring, R-cube. ML-KEM and ML-DSA, both of them are based on module lattices. So it has a ring. They are based on rings, actually. Excuse me, vector spaces are based on fields, and modules based on rings or rings. So we have this ring for ML-KEM, R-cube. It means that we have a polynomial. Every element in these schemes, in these two schemes are polynomials. For ML-KEM, we have a polynomial of degree 256. It means we have 255. It means that we have 256 coefficients, and each coefficient is between 0 up to 3328. So arithmetic are based on are modulo 3329. We have three security standards for ML-KEM: AES 128, 192, and 256. And ML-DSA is a digital signature scheme based on MLW and another hard mathematical problem, self-target MSIS. And it uses another ring. As you can see, the modulo in ML-DSA is much larger than ML-KEM, about 8 million. But again, the number of elements, the number of coefficients is 256. And there's 3 security levels.
I have one question.
Yeah.
So why did you write the security levels in terms of SHA, AES, and...
Actually, we have 5 categories, not 3 categories: AES 128, 192, 256. We have AES 128, SHA 256 for brute force attack. SHA 256 is equal to AES 128. But in collision, there's a difference between AES 128 and SHA 256. There's a difference between these two. Because in ML-DSA, sometimes we are looking for collision attacks. So SHA 256 is a little different is a little harder and is a little more secure than AES 128. Okay. AES 128 is category 1. SHA 256 security level is category 2. So both of them uses polynomials. And for polynomial arithmetic, we have polynomial addition, polynomial subtraction, and polynomial multiplication. Polynomial multiplication is a bottleneck in these 2 schemes, both of the schemes. These schemes have lots of blocks like hashing and compression, decompression, packing, unpacking. but most of them are straightforward, except polynomial multiplication. Polynomial multiplication is the hardest part in these schemes. So we need a solution to overcome this challenge. So this is a high-level overview of ML-KEM and ML-DSA. As you can see in keygen, we have A is a matrix of 2 by 2 or 3 by 3 in ML-KEM. So a matrix, each element in this matrix is a polynomial. So each element in this matrix is a polynomial of degree 255. It means we have 256 coefficients, and each coefficient is between 0 up to q minus 1. Use the modulo in ML. So S is a vector of 3 elements. So for multiplying A times S, we have to multiply 9 polynomials together for just key generation, polynomials of 256 coefficients. So it is a very expensive operation here. And we have another multiplication in decapsulation, another multiplication in encapsulation, another multiplication. We have 2 multiplications in encapsulation for ML-KEM. And for ML-DSA, we have 1 multiplication here, another multiplication in signature generation, another multiplication. We have two multiplications of polynomials in signature generation. Boldface means it is a vector or a matrix. Boldface, small letter, it means a vector of polynomials. Boldface, like A. Capital means a matrix of polynomials. C is just 1 polynomial, so it's not bold. And we have another 2 multiplications in verification. So we have lots of polynomial multiplications in post-quantum cryptography systems. And let's see how we can do this. So if we want to use a schoolbook method to multiply 256 element by 256 element, we need 256 times 256 multiplications. It means 2 to the power of 8 times 2 to the power of 8, 2 to the power of 16. We need approximately 65,000 multiplication for if we want to use schoolbook method for just 1 polynomial multiplication. So we cannot use this. The solution to this is NTT, and let's talk about NTT a little. So NTT, if we want to multiply these 2 polynomials, we can use this equation here. It's negacyclic convolution or negative wrap convolution. It's a special type of convolution for this ring. It can multiply two polynomials and reduce it over x to the power of n plus 1 at the same time in 1 step. But how many multiplications do we need here? Still n squared. So the time complexity is still the same. So it doesn't solve anything. But we know that Fourier transform can compute convolution faster. So we can use Fourier transform, a generalized version of Fourier transform to compute this convolution faster. Generalized version of Fourier transform over the finite field or over finite rings is entity, number theoretic transform. So if we can use entity, we can convert each element, each polynomial into the entity domain and do the pointwise multiplication in the entity domain and convert it back to the normal domain. And unlike Fourier transform has some meaning. It means that we have what is the amplitude in this frequency. So the order of elements is important in Fourier transform. But here, number theoretic transform doesn't have any meaning. It's just some tool to do this multiplication. So the order of elements in entity doesn't important. We have just one standard announced by the NIST. We have to follow that. But we can convert a polynomial to the entity domain with different algorithms. And the result would be different. Not just the order, but also the values. The values may be different. But we have one standard for that. And we have to follow this standard. So for entity, like Fourier transform, we have 2nth root of unity. In Fourier transform, we have infinity or root of unity just one root of unity. But here we have 2n root of unity for entity. It means that z to the power of 2n equals 1, and z to the power of n equals -1 modulo q. So we can convert, if we want to multiply these two polynomials, a and b, we can convert a to the entity domain and b to the entity domain, do the pointwise multiplication, and convert it back. So we have the result. And actually, we have to, in the end, we have to, or in the middle, we can do that in the middle. We have to reduce it over modulo q. So we have to reduce modulo x to the power of n plus 1 and reduce modulo q.
So yes. These roots of unity, they are already mod q, right? So if you do the operations, it's over mod q.
No, for example, 3 and 5, both of them are less than 7. But 3 times 5 is more than 7. Maybe both numbers are less than q, but the multiplications would be more than q. So we need to reduce it over.
Saying like these elements are over zq by definition. So when I'm doing the multiplication and whatnot, these mod q operations are already associated with it.
Do you mean in Sage Math when we define it over a ring and we multiply that over the? This is in Sage Math, not in hardware.
Yeah.
In hardware, if you want to multiply two, for example, 12-bit number, the result would be a 24-bit number. In hardware, we don't have any fields, rings that has already been defined. We have to do it by ourselves. So, and this is the thing that we'll talk about this today. So the equation for entity is this. Like Fourier transform. In Fourier transform, we have e to the power of negative jk over n. Here we have the entity for that convolution. And the identity is somehow like entity equation, but it has inverse of n, not q actually. Inverse of n multiplied as a scalar factor. But the time complexity is still n squared. So for this, exactly like fast Fourier transform, we have two butterfly units, Kulitukki and gentleman's sum. Kulitukki for entity and gentleman's sum for identity. If you write down this equation here, because of this property, that the power of 2n is 1 and the power of n is -1, you can simplify this equation and find some patterns of converting it to a recursive algorithm, to a divide and conquer algorithm. So we have these two butterfly units. It gets two values, u and v, and the result would be three values actually, u and v and z to the power of something. And the result is u plus v to the power of zeta, v times z to the power of k, and u minus v to the power v times zeta to the power of k. So this is Kulitukki butterfly unit. And gentleman's sum is u plus v and u minus v times zeta to the power of k. So we have to do, this is the most important part in entity implementation on hardware. We have to implement this multiplier here, this modular multiplier here, v times zeta to the power of some number, and addition and subtraction. So these are the basic elements of hardware implementation. And we can integrate these Kulitukki algorithm, Kulitukki butterfly unit and gentleman's sum here in entity Kulitukki. So we have, for example, we have these 8 points. We want to convert 8 point to another 8 point for entity. These are the coefficients of a polynomial of degree 7, for example. This is an example. A0 up to A7, and it gets A0 and A4 in the first stage. And output would be A0 plus A4 times zeta to the power of 4, and A0 minus A4 times zeta to the power of 4. And the result would be in these two places. So this is in-place entity computation, because the result, the output, the memory locations of the outputs are exactly the memory locations of the inputs. But the problem with this algorithm has been standardized and announced by NIST. So the order of the input should be like this: A0, A4, A2, A6. This is a bit reversed order. The output order has to be like this, exactly like this. So we can have another algorithm to compute entity, but the order should be this: A0, A4, A2, A6, a bit reversed order. But the problem with this algorithm that, this is my personal opinion, the problem with this algorithm is, let me say one thing before problem. It converts 8 points to 3 stages, log n, log the number of these points. Log 8 is 3, so it converts it to 3 stages, and each stage needs 4 multiplication. So how many multiplication, instead of 64 multiplications for a polynomial of degree 7 or polynomial with 8 coefficients, instead of 64 multiplications, we have 3 times 4, 12 multiplications. So the time complexity is n log n, and this algorithm is much faster. But the problem is, in the first stage, the spacing between these two pair of these two inputs are 4, half of n. And in the next stage, the spacing is 2. The next stage, the spacing is 1. The spacing between the memory locations of inputs and outputs are different among the stages, among the different stages. In software, this is not a problem. We can implement it on software very easily. It's not that important. But in hardware, I find it a little difficult to implement it. We have another algorithm. For INTT, the first stage is 1 and 2 and 4. And if you have 256, 1, 2, 4, 8, 16, up to 128, the spacing between the inputs and the outputs. And finally, we can multiply by inverse of n. And we can integrate this multiplication by inverse of n among the stages. If we multiply after this addition and subtraction, if we multiply the output by inverse of 2, inverse of 2 is a inverse of 2 mod q is a constant number. So if we want to multiply by inverse of 2 in the first stage, and in the second stage, and the third stage, so we multiply it by inverse of 8. This is the thing that we want here. N is 8. N is the number of points. So if we multiply by inverse of 2, inverse of 2, inverse of 2, the result would be multiplication by inverse of 8. So it's better to multiply the output of the addition and subtraction in each stage by inverse of 2, instead of having another clock cycle and another stage for multiplication by the inverse of n. Because multiplication by inverse of 2 is very easy, and we will see that. So it makes it much faster. The time complexity is n log n. To convert to the polynomial, to convert the polynomial to the entity domain, the time complexity is n log n. Actually, the number of the number of multiplications are half of n times log n for converting to the entity domain. For the point point multiplications, we need n multiplications, and for the inverse, we need half of n times log n. So the dominant term here is n log n, and the asymptotic time complexity would be n log n. For multiplication of 2 polynomials using entity. And instead of 65,000 multiplications, we need 2,000 multiplications. So it's much better. And this is the whole scheme that we have to use. Convert one, we have this A and B in this ring. So both of them have 256 elements. A0 up to A255. Convert it to the entity domain. A hat is the entity version of A. We have another 256 numbers. B, another 256 numbers, and we multiply it pointwise. So C0 would be the result of the multiplication. C0 would be A hat 0 times B hat 0. C hat 1 would be A hat 1 times B hat 1. So it would be much faster. And finally, we will convert it back, this term to the normal domain. And we have another scheme inspired by P's FFT. In this algorithm, the spacing between the pairs are the same among all of the stages. The spacing between the pairs for entity is 4 for inputs, or 4, 4, 4 for all of the stages. And for the output, the order is different. So it reads from 0 and 4 and writes into 0 and 1. And reads from 1 and 5 and writes into 2 and 3. So this is out of place entity computation, unlike in-place entity computation. And this is the integration of multiplication by half of n. We can multiply by half of n after each addition and subtraction. Excuse me, not half of n, a half. Multiplication by a half, 1/2.
Here you change the order of n.
And the final order is the same,
Yeah,
but the intermediate orders is different. Yes.
yeah.
Yeah. Here, after the first order, for example, here, after the first order, these two numbers are here. The results are in 0 and 4. But in constant geometry, the results are in these two locations. It writes into another different locations. But the final order would be the same, exactly like in-place entity computation. But this makes some problems for us, for ML-KEM, not for ML-DSA. For ML-DSA, we have to go over all of the stages. So the final results are the same. But for ML-KEM, we have one less stage. So as I said, the intermediate stages are different. The values in here are different. So in ML-KEM, it makes some problems, and we will talk about that. So let's talk about the differences and similarities between ML-KEM and ML-DSA. So the ring for ML-KEM, as I said, is this, and ML-DSA is another. So both of them has 256 elements. Both of them uses module-lattices. Both of them uses rings. Both of them uses polynomials, and both of them has some similar hardware blocks or mathematical blocks. Both of them use hash functions, shake and SHA theory. And both of them use TRNG, true random number generator, or pseudo random number generator. And as you may expect, because ML-KEM and ML-DSA use rings, NTT, INTT, PWM, point multiplication, addition, and subtraction are similar between them. But what are the differences? As you know, they have some. ML-KEM and ML-DSA have some similarities, similar blocks, have some different blocks, some shared blocks, and some dedicated blocks. So it's not very strange. But the main problem is because the different moduli between ML-KEM and ML-DSA. First, in ML-KEM, 3329 has only 12 bits, but ML-DSA, this number has 23 bits. So the data width of the bus that we want to use our hardware implementation would be different if we want to implement a unified hardware. But it exposes us another problem, this different moduli, that for this number, 8,038,000, we have to nth root of unity. So we can use the entity. But for this number, 3329, we cannot find any 2nth root of unity. We cannot find any number that can satisfy that equation. We can find a number that satisfies nth root of unity. We can find nth root of unity, but not 2nth root of unity. So we cannot use the complete version of entity for ML-KEM. We have a solution for this. ML-DSA converts 256 numbers or one polynomial of degree 256, excuse me, to 255, to 256 polynomials of degree 0, or 256 numbers, 256 constant numbers. But ML-KEM, using ML-KEM, we can convert it to 128 polynomials of degree 1, like ax plus b. This is a solution for this modulo for ML-KEM. So if we want to convert it, actually here we have a polynomial of degree 8. And converts it to 4 polynomials of degree 2 here in this stage. It converts it to, after this stage, 4 polynomials of degree 2, 2 polynomials of degree 4, 4 polynomials of degree 2, and 8 polynomials. Here we have 8 polynomials of degree 0, 4 polynomials of degree 1 and 2 polynomials of degree 2. Yeah. So we have 2 polynomials of degree 2, 4 polynomials of degree 1, and 8 polynomials of degree 0. But if we skip this stage, the last stage here, if we skip this stage, the result would be 4 polynomials of degree 1. And another problem would be PWM, because we want to multiply 2 polynomials of degree 1, not like this in PWM. We cannot multiply A0 times B0. We have A0x plus A1 and B0x plus B1. So the result would be C0x plus C1. And C0x plus C1 would be A0x plus A1 times B0x plus B1. B hat, actually. And reduce it modulo x to the power of zeta to the power zeta x times zeta to x minus zeta to the power of 2 times bit reverse of I minus 1 plus 1. So we need to multiply these two and reduce it over a reducible polynomial. So we will see that, how it works. So for entity, it has one less stage. Instead of, for example, for ML-KEM, instead of 8 stages, we have 7 stages. We skip the last stage. And for identity, we skip the first stage. But for, as you may expect, for constant geometry, the output would be different. The order in the output would be different if you want to use constant geometry. And if you want to use constant geometry for identity, the order of reading from the input for the first stage would be different. So this is the equation C2I after reducing over that irreducible polynomial. We'll get to this. For example, C0 would be A0 times B0, A hat 0 times B hat 0 plus A hat 1 times B hat 1 times zeta to the power of 2 times bit reverse of I plus 1, which bit reverse of 7 plus 0 plus 1, I is 0. And C hat 1 would be A hat 0 times B hat 1 and plus A hat 1 plus A hat 1 times B hat 0. And we will get the final result. So PWM of KEM has 5 multiplications. 1 multiplication, 2 multiplication, 3rd multiplication, 4th multiplication, and 5th multiplication. We have 5 multiplications here for PWM. So for a unified hardware for our design, this is one scheme that you can use. It has a K-chuck unit for hashing, for using SHA-3 or shake. We have centered binomial distribution, sampling or uniform sampling, and we have rejection sampling. We have different types of sampling for ML-DSA, rejection sampling for ML-DSA, and CVDA uniform for ML-DSA and ML-KEM for both of them. SHA-3 and shake will be used in both of ML-KEM and ML-DSA. And we have a true random number generator or pseudo-random number generator here. We have several dedicated blocks for ML-DSA, hint unit, decompose unit, and pack or unpack unit. ML-KEM, it compresses or decompresses the value for both security and reducing the number of bits and increasing the efficiency, encoding and decoding to adapting to the current handshake schemes. We need a memory. We need a memory here for RAM, ROM. We want to compute. If we want to store all of the powers of zeta here, because here we want to store zeta to the power of 4, 2, 6. Zeta is a constant number. For ML-KEM is 17. For ML-DSA is 1738. If I'm not wrong, 1738. I think. Yeah. So the powers of zeta are constant. So we can pre-compute all of them and store them in one RAM. Or we can use on-the-fly Twiddle factor computation. On-the-fly Twiddle factors are powers of zeta. We can use on-the-fly fiddle factor computations. Just store zeta or some powers of zeta and compute another powers of zeta from the stored values. Or you can compute all of them, pre-compute all of them, and store them in one read-only memory. But our focus today would be this part. As I said, the other parts are pretty straightforward. You can do some optimizations in other parts, but the most important part, the bottleneck of these schemes are this part, polynomial arithmetic unit. We want to convert A and B to the entity domain in the most efficient way. We want to reduce it over Q, the modulo Q, in the most efficient way. We have several algorithms for reducing over Q, Barrett's reduction, Montgomery reduction, Planter reduction. We have several reduction algorithms that has been introduced especially for these numbers, for ML-KEM and ML-DSA. So let's see how we can implement this on hardware in the most efficient way. So our focus, as I said today, would be on a unified design, a design that can support both of them using a single core. But I want to talk about these are my three papers: light entity, night core, and hyperpoly. Hyperpoly is the unified design, so we will focus on hyperpoly today. Light entity is for conversion of one polynomial to the entity domain, or identity converted back using identity for ML-DSA. Night core for ML-KEM, and it can do PWM. They are both are not a complete design. Light entity can only convert to the entity domain and convert it back to the identity domain. As you will see in most of the papers, they convert only to the entity domain or identity domain, because this is the most important part, not just PWM. But integrating all of them in just one hardware is a whole another challenge. If you want to have a hardware that can do all of them, converting to the entity, identity, do the pointwise multiplication, do the addition of polynomials, and do the subtraction of polynomials. So I want to talk about a little about light entity and night core because it has some insights to how we can reach to a unified design hyperpoly. So in light entity, our goal was the smallest possible area for ML-DSA, for entity and identity. It uses constant geometry because constant geometry simplifies the control unit. Control unit doesn't need to change the locations of inputs and the outputs for ML-DSA. And for conflict-free reading from memory and writing into memory, we have a pinpoint RAM architecture that reads from one RAM and writes to another RAM, and then reads from this RAM and writes back to the first RAM. So we have two dual ports RAMs here, and read from one of them and write into another one. And then we will read from the second one and write into the first one. So let's see how we can multiply by half. If we have an even number, multiplication by half is very easy. Shifting to the right by 1 is very easy. But what about if it's an odd number? You can add the number to Q. You can add Q to the number. Actually, you can add Q to the number, and then shift it to the right by 1. So this is the thing that I said, multiplication by inverse of n. Here, multiplication by inverse of n would be difficult. And it's not that difficult, but it needs another clock cycle, another stage for multiplying by inverse of n. But multiplication by half, here, it's much easier. It's just one shift or one add-on shift. So we have to use only this method. So we have this hardware for light entity that can do the addition and subtraction, and if it was for I entity for inverse, because multiplication by half of n is only for multiplication by half of n is only for for I entity, for I entity. Only for I entity. So we need a block that can that gets two inputs, add them together, subtract them from subtract the second one from the first one, and if it is for I entity, multiply it by 1/2. So A and B, and add them together and reduce it over Q. Reduce it over Q is very easy. If A plus B is more than Q, subtract Q from that number. If it's not more than Q, so it's already reduced over Q. Because both of them are less than Q. So the result would be at most 2Q minus 2. The A and B could be Q minus 1. The maximum value of A is Q minus 1. Maximum value of B is Q minus 1. So the maximum value of A plus B is 2Q minus 2. So it's less than 2 times Q. And by reducing Q just one time, we will get the final, the correct result. And if it's for I entity, shift it to the right one time by shift it to the right by 1, or add Q to that, and then. And for modular multiplication, in this paper, I have studied several modular multiplications, and I saw that Bardia reduction was the best one. And Bardia has some property that I like, is the final result of Bardia reduction doesn't have any scalar. For example, for Montgomery, the result of A times B mod Q would be A times B times R inverse of R mod Q. So we have a scalar. We have some methods to overcome this R inverse of R. For example, for entity here, for here. The multiplication here, the multiplications for butterfly unit here, for entity and for I entity. As you see, the multiplications are by a constant number because we know zeta and we know powers of zeta. So we can multiply these powers of zeta to R. And after multiplying, and we store the multiplications of zeta times R in the memory. And then when we reduce it over using Montgomery, zeta times R inverse, R and R inverse would cancel each other out. So we can overcome this. Or another algorithm that has been studied widely. But this is not the case for PWM. In PWM, we have A times B, and we don't know the value of A and B. The value of A and B are variables. In PWM, we want to multiply A hat 0 times B hat 0. So we cannot use a pre-scaling here. We have to integrate the pre-scaling into the Montgomery. So it would complicate our hardware. And Bardia reduction was the best one. And we don't use any multiplications for the Bardia reduction. For Bardia reduction, we need mu here, a constant value, 2 to the power of 2 times the number of bits, which is 23 for ML-DSA. But we can rewrite mu as this, some powers of 2. And it's a very good approach, because if we want to multiply one number by mu, we can just shift that number 23 times, plus shift that number 13 times, plus shift that number 3 times, minus that number. So this is x2, this is x1 times mu that you saw on Bardia reduction. But we do all of the multiplications by shifting and adding, which is a very more efficient way. And here we are multiplying S times Q. We don't multiply S by Q. We use shifting and addition. So it would be much faster and much smaller. It makes our design much smaller if we want to use only shifting, because shifting and adding are free. They are very small, and they are very, very fast. And this is a ping pong memory that you will see in most of the papers, reading from one RAM and writing to another memory. And this is the whole design. We have one RAM storing powers of zeta, two RAMs reading from this one, writing into this in first stage, reading from this and writing into the other one. And we have one modular adder and subtractor and one modular multiplier that used Bardia reduction. And we have another core, another design night core that can do NTT and ITT and PWM for ML-KEM. And because PWM for ML-KEM is a little harder. So I will go faster over these slides here. We have three challenges. We need to adapt the CG constant geometry entity for the ML-KEM. For this, we only reorder the outputs for the final stage. Only for the final stage, we write into different locations. And for identity, we read from the different locations to overcome this challenge. For PWM, we need to add the capability. So we don't need any additional hardware for adopting constant geometry for ML-KEM. For capability of PWM, we don't need any additional hardware because we can do that using that modular multiplier here. We can do the we can do the PWM only using this. Just some additional logic to the to our control unit. But what about twiddle factors? We need to store some other powers of twiddle factors. We have this mathematical property here. So we can use the previous stored powers of zeta to compute the PWM. Because here in this, it is zeta to the power of bit reverse of I. Zeta to the power bit reverse of 0, zeta to the power bit reverse of 1, bit reverse of 2, bit reverse of 3, up to bit reverse of 255. But for PWM, we need to store power of zeta to the power of 2 times bit reverse of I plus 1. But because of some properties of zeta, zeta to the power of 2 times bit reverse of 2 times I plus 1 is this. It's already stored in the memory. So we can use those numbers. So we can add a PWM capability to our design for PWM without any additional hardware, just some additional logic for the control unit. It makes our design a little larger, but not like adding another multiplier for our design, adding another hardware, another big hardware, another important block to our design. Maybe the number of lookup tables, for example, before this additional logic for our control unit. The number of lookup tables is, for example, 550, and after this additional logic, it would be 650. So, and this is the hardware design for night core. And as you can see, it's exactly the same, just some colors are upgraded. But we have just one additional signal here, PWM, for control unit. But all of the hardwares are still the same. So in our design, hyperpoly, which would be after this very long introduction, which would be our focus, how we can integrate both of them in just one single core. We want one single architecture that can compute both of them, ML-KEM and ML-DSA, in just one core. Not we have 2 cores, one core for ML-DSA, because if you want a chip for cryptographic goals and for your cryptographic application, you need both of them. You need both digital signature and key exchange mechanism, not just you don't need just only key exchange mechanism is not enough. You need both of them for a chip, for a secure chip, for root of trust chips. So we need to implement both of them. And if you want to implement one core for ML-DSA and another core for ML-KEM, your design would be much larger. It's not efficient. We need one core that can do both of them. So what are the challenges? We want a hardware that supports both of them, this queue and this queue for ML-KEM and ML-DSA. So we need a data path that can support both of these queues. And we need a core that can do all of the required operations for polynomials. And our design should be small and fast, both of them. Sometimes our focus would be on speed. Sometimes our focus would be on area. In night core and light entity, in these the previous designs, our focus was on area. Here, our focus is on speed. We want a design that is as fast as possible. For example, for servers, we want a server that can do both of them, digital signature and encryption, at the same time, as fast as possible. For example, for some applications in servers, as I said. So this is an architecture for our memory. We have two memories here. For entity, two memories of 128 and 24 bits. So each row has 24 bits. So in each row, we can store two coefficients of ML-KEM, because each coefficient of ML-KEM has 12 bits, or one coefficient of ML-DSA. Each coefficient of ML-DSA has 23. So like this. This is A0, A1, A2, A3, A4. All of the coefficients of one polynomial of ML-KEM is stored in one of these. So in these two RAMs that we have here, we can store two polynomials of ML-KEM, or one polynomial of ML-DSA in all of them, in both of them. For ML-DSA, this is the 24 bits, A0, A1 up to A127. We have up to A255. So this is for the first one, from 0 up to 127 and 128 up to 255. So, how we can manage both of them? For example, for multiplication is the hardest part for a unified design. So it doesn't matter if it is for ML-KEM or if it's for ML-DSA. We compute all of this. We divide A to left, the 12 bits of left and 12 bits of right, and B to we divide it to two parts, to half of BL and BR. We compute PL and PR, multiplication of AL times BL and AR times BL, and PRL, PL plus PR. And this multiplication, we compute all of these 5 multiplications. And this reminds you of what? Karatsuba. We can use this to use a Karatsuba multiplication. If it's for ML-KEM, AL is one coefficient, AR is another coefficient, BL is one coefficient, BR is another coefficient. Yeah. So AL times BL would be the result of the multiplication of first coefficients, and AR times BR would be the multiplication of the second coefficients. So PL and PR are our results. So we have our results for ML-KEM. But what about this for ML-DSA? We have PL and PCRL here, PL and PCRL and PR. So using Karatsuba algorithm, we can get the whole multiplication of A times B. So for ML-DSA, we want to multiply A times B. For ML-KEM, we want to multiply AL times BL and AR times BR. So this is the best method for a unified design that can support both of them. A data path of 24 bits and use this. So for PWM, we had, as you saw, we had this algorithm, this equation for C2I. And for C had 2I plus 1, we had this. We can rewrite this as this one. And how can it help us? We have all of this. If we want to multiply A times B, we have this already. This is AL plus AR times BL plus BR. We have all of this. AR plus BL times BR plus BL minus PRL. Minus PL plus PR. So this is PL, this is PL, and this is PR. So we have C had 2I plus 1 as PCRL, or we have it already. And what about the first one? We have this term in our multiplications, and we have this term in our multiplication. So we can multiply it by zeta and add it to in one clock cycle and add the result to the other. So in 2 clock cycles, we will get the result of PWM. So it's very fast. And this is our hardware. We need some consideration. This hardware is a little large because we need some considerations for constant geometry for ML-KEM. We need to map some of the inputs for ML-KEM here and some mapping for output of entity and for identity of ML-KEM. Entity of ML-KEM in the input, entity of ML-KEM in the output. So the conclusion is the most important problem for us is ML-KEM use a 12-bit modulo and ML-DSA use a 23-bit modulo. So we need a flexible data path. So for this, we can store one ML-DSA or ML-DSA polynomial in memory or 2 ML-KEM coefficient. And in our design here, it's a parallel design, so it's very big. It has 128 butterfly units, and these butterfly units are for Kulituki or Gentleman's Son, and we have to have a hardware with both of them. A unified design that should a unified butterfly should have a capability of entity and identity. And and another important problem is ML-KEM uses incomplete entity. Instead of 7 stages, it has 7. Instead of 8 stages, it has 7 stages. And okay, so for future work, for small designs, you have to implement side channel countermeasures, and side channel countermeasures would enlarge your design considerably. There's one design, Calyptra, for triple alliance between Microsoft and AMD and NVIDIA and many of them. And before side channel countermeasures, it has 5,000 lookup tables. Excuse me, 40,000 lookup tables, and after countermeasures, it's right now 300,000. Excuse me, 330,000. 330,000. So it would be much larger. And we have to implement it on ASIC, and the full ML-KEM and ML-DSA would be our next goal. So entity is the most important one on the bottleneck, and unified design is required for our design. And mathematical properties of zeta and other parts would help us to increase the efficiency and reduce the area. And the last thing is post-quantum transition requires all of them. We need to study all of them. Thank you for having me in this session. If you have any questions.
Questions online? I don't see. Okay, if not, let's thank again for this talk. So this is what we have for the day, and if you have any question, you can ask him in person. Okay, so how should I close it?